Okay, seems we're ready to go. So welcome again to the last session of the day. This is the isogeny session. We have two extremely interesting talks. The first one will be delivered by Luciano, who will talk about an algorithmic approach to 2-2 isogenies in the theta model. Luciano.
And applications to isogeny-based cryptography, because we are in the isogeny session. This is joint work with Pierrick Bertois, Giacomo Pope, and Damien Robert. So, okay, let me start. Okay, it works. So, the first thing to talk about is why? What's actually the main motivation behind this work? Is everything fine? Okay. I see people waving. No. Okay, yes. So the main motivation behind this work. So the main motivation was let's look at the SIGC attacks. And in the case of these attacks, the main building block for these attacks was the computation of chains of two isogenies between elliptic products. These elliptic products could be in dimension 2, 4, or 8. And depending on the dimension, you have specific formulae to compute these isogenies. In the case of dimension 2, specifically for these attacks, to compute these isogenies, you need a combination of the so-called Richelieu formulae and some specific algorithm to compute for the gluing and the splitting. Don't worry, I will go back to this in the next slide. Then, soon after the attacks went public, researchers soon realized that this could have been used as a powerful tool in isogeny-based cryptography. And in particular, the main byproduct of these attacks was that now we have a new representation for isogenies between elliptic curves. In particular, it means that we actually have some concrete applications. So just to name a few, in the case we have some chems, like Festa and QFesta, and if you were there for the talks on Tuesday, you may have heard of the new key sign variants. So given that so many applications use this building block, computing these chains of two isogenies between elliptic products, then the main problem and the main motivation that we had for this work was so since we want to construct crypto systems, we said that it became evident that we needed a faster way to compute these two isogenies between elliptic products. Okay, so let me give some background, because in the case of dimension 2, things are a little bit more explicit than general dimension. So in the case of the SIGC attacks, what we needed was a generalization of elliptic curves to higher dimension. And whenever a natural generalization of these elliptic curves to higher dimension are the principally polarized abelian varieties. A lot of words, many complicated words, but in the case of dimension 2, actually we have some concrete description. In particular, in the case of dimension 2, we have two models. The first model is the products of elliptic curves. So basically you take two elliptic curves and you consider all the pairs of points on these two elliptic curves. And the second model is actually Jacobians of genus 2 curves. And here I've just sketched a little bit what's kind of the shape for these genus 2 curves. Whenever you consider isogenies between these principal polarized abelian surfaces, in most of the cases, in the cases interesting at the moment for cryptography, these isogenies have kernels of rank 2. And in particular, we will say that an isogeny is between surfaces is an NN isogeny if its kernel is isomorphic to Z mod n times Z mod n. Okay, so let's talk a little bit about what's the main goal of this paper. The main goal is to compute these 2 to the n, compute these NN isogenies, and specifically n is of the form a power of 2. In particular, we are going to compute 2 to the n isogenies between elliptic products. How do you compute these isogenies? This is analogous to the case of elliptic curves. Basically, you compute you chain two isogenies, which are actually the atomic entities whenever you want to compute these long chains of isogenies. So let's look a little bit about how this single isogeny look like. So the first isogeny that you will encounter is an isogeny mapping from an elliptic product onto a Jacobian of a genus 2 curve. And in this paper, we make the assumption that all the abelian surfaces that you are going to encounter along this path of like two isogenies are basically just Jacobian of genus 2 curves. This is not restrictive because, I mean, in the case of, for the applications that we had in mind, we just wanted to consider like the isogenies which are relevant for isogeny-based cryptography. And making this restriction, we obtain some kind of faster algorithms compared like to the general case. Okay, so let's look at like at this chain. The first isogeny, the isogeny phi1, is the isogeny mapping originating from an elliptic product and mapping onto the Jacobian of a genus 2 curve. There were like already formulae to compute these types of isogenies, and in particular, like a reference for these formulae are basically can be contained in Hall, De Proust, and Pullman, a paper from them from the 2000. And then another special isogeny is the last isogeny, the so-called splitting isogeny. What does it mean? It means that it originates from a Jacobian of a genus 2 Jacobian of a genus 2 curve and maps onto an elliptic product. And also in this case, there were formulae, and all the remaining isogenies are isogenies between these Jacobians. These isogenies, there were already formulae to compute these isogenies, and these formulae were based on like these so-called Richelieu correspondences. These are the Richelieu correspondences are kind of like an old result by Richelieu, but for like a more modern like treatment of these isogenies, you can look at like Ben Smith's PhD thesis. Okay, so this was like the state of the art before we started to work on this problem. So from like a cryptanalytic perspective, computing these chains of two isogenies using like these techniques was just fine, because I mean, you don't need it to be fast. But now, given like all the new applications that we have in mind, we decided to look like in a different way to compute these isogenies. And one natural candidate was to look at this theta model. This theta model is nothing new to the cryptography. Indeed, the theta model, at least in disguise, was used in the case for like to have like efficient arithmetic in the case of elliptic curve cryptography and also like hyperelliptic curve cryptography. In this case, I mean, the formulae were tailored to perform just arithmetic on these abelian varieties, but we tweaked those formulae and adapted those formulae to our use case. And then, adapting this formulae to our use case, we obtained that compared to the state of the art, the codomain computation is actually 10 times faster than the strategy that I showed you before, and the isogeny evaluation is actually 20 times faster than what we had before. What's the overall like result that we have at the moment? Then now we can compute cryptographic size, let me allow to say this, isogenies, in a matter of milliseconds. Okay, so I've said like, I've just talked a little bit about this theta formulae, but what's like a theta structure? So let's start having just a principally polarized abelian variety surface. So just for the sake of having something explicit in mind, let's just imagine that it's just the Jacobian of a genus 2 curve. Then on this abelian surface, we take a symplectic fourth torsion basis. What's this? Basically, you take your fourth torsion for your abelian surface, and you decompose this fourth torsion into two subgroups. The first one is generated by S1 prime and S2 prime, and the second one is generated by T1 prime and T2 prime. Then, once you have these generators, the condition to being symplectic means that the pairing between S1 prime and T1 prime is equal to the pairing of S2 prime and T2 prime, and this is equal to basically a primitive fourth root of the unity. And all the remaining pairings should be trivial, and this is the condition to be symplectic. Once you fix this symplectic fourth torsion basis, you automatically obtain like four functions. These functions are called the theta functions, and they're indexed by 0, 0, 1, 0, 0, 1, 1, 1. There is a specific reason why those functions are indexed in this way. But, I mean, like, you obtain these functions, but once you reorder them, you will obtain like analogous formulae. What I'm trying to say is that basically, in this paper, we just fix this ordering, but if you pick another ordering, you will obtain some formulae which basically will look the same. And once you have these functions are mapped from like the principally polarized abelian surface onto P3. And once you take a point P and you evaluate all these functions at this point P, you obtain a new representation of this point. And this representation is called like the theta coordinates of this point. So if you take like, here I've put an example. So if you take like the Jacobian homogeneous 2 curve, and then you consider like the map, the equation that you obtain mapping these points using these functions here, you will obtain a representation of the Kummer surface, and which is actually which is there like on the side of the slides. And very important, like the projective point, when you evaluate all this theta function at the identity, you obtain a really special point. This point is called the theta null point, and this point is enough to describe the whole abelian surface. Okay, so these are actually the fundamental notions that we need. Okay, now let me introduce like the formulae. This formulae, I mean, like maybe the theory to understand all the mathematical details can be complicated, but concretely what you need to compute these isogenies, you just need like 3 operators. The first operator is the Hadamard transform. Roughly speaking, the Hadamard transform is just a matrix multiplication. And once you have like a point represented in theta coordinates, and you apply the Hadamard transform to these theta coordinates, you obtain the dual coordinate, you obtain like another special way of representing this point, which is called the dual coordinates of P. Another special property of this the Hadamard transform is that if you apply the Hadamard transform twice, then projectively you obtain the same exact point. So this is the first operator that we need. The second operator that we need is the squaring operator, which, as the name suggests, it just takes each component and squares all the components. And then the last operator is the star operator, which is just the component-wise product of the two vectors. Okay, so now let's just find a way to how to use these operators to obtain isogeny formulae. So the main ingredient that we have to obtain this formulae is actually the duplication formula. So you start from a symplectic fourth torsion basis of your abelian surface. And then, as I said before, you will obtain like 4 theta functions. And then let's consider the isogeny phi originating from A and mapping onto B, another abelian variety, surface. And suppose that the kernel of this isogeny is generated by T1 and T2, where Ti is basically twice Ti prime, which is the second group in the symplectic fourth torsion basis. In that case, you have that for all points P and Q in A, you have that the star product between the theta coordinates of P plus Q and P minus Q is equal to the Hadamard transform of the dual theta coordinates of the star product between the dual theta coordinates of phi p and phi q. So this is actually the main relation that we use in the paper. And then playing around with this relation, then you can derive classical like addition formulae, completely analogous to the case of like the Montgomery arithmetic. And the cost of like this formula is basically for differential addition, you have 8 squares and 17 multiplications, and doubling is 8 squares and 6 multiplications. the formulae that we obtain here are basically the same formulae as the one showed by Gaudery in a paper from 2005. Okay, so now let's use this formula, the duplication formula, to compute isogenies. So again, suppose that we are in this scenario. We want to compute this isogeny phi, whose kernel is equal to T1, T2, is equal to the group generated by T1 and T2, and Ti is basically just twice Ti prime. In this case, we also assume that we have an isotropic group, so actually you can relax this condition, and I will tell you a little bit about this later on. So suppose that we have a group, like we have like two torsion above this Ti prime, and in this case, when you apply, okay, sorry, another definition. You define like the dual theta null point, you define it by alpha, beta, gamma, delta. And once you have all of this, and you take the theta coordinates of the points T1 second and T2 second, then you take these theta coordinates and you apply the square and the Hadamard transform, then you will obtain some relations between like the dual theta null point and some unknown like scalars. Yeah, scalars are x, y, z, w. And here you can see that playing a little bit with this kind of relations that you obtain evaluating this theta coordinates, you can actually recover the dual theta null point. The dual theta null point is basically just the tuple given by alpha, beta, gamma, and delta. And then once you have this dual theta null point, you can reapply again like the Hadamard transform, and then you obtain a theta null point for the abelian surface B. And as I said before, once you have like the theta null point, you actually have like a full description of your image abelian surface. And this is actually basically the main idea behind this isogeny formula that we describe in the paper. Okay, so let's talk a little bit about some concrete costs. So here with S, I mean like the cost of squaring, M for multiplication, and I for inverse. The formula, all the results that I've shown you before basically work projectively, and which means that you can projectivize all the formulae, and in particular, the formulae, the algorithm to compute the doubling of a point and the algorithm to compute the codomain of an isogeny actually share like some common pre-computations. Once you arrange things in a proper way, you obtain that these are like the costs for like the codomain evaluation and the evaluation of the of an isogeny. And here in the last row, I mean there is like a different row dedicated like to the first isogeny, which is the gluing isogeny. In this case, the situation is a little bit more complicated, and as you can see, there are some additional costs for like this special isogeny here. As I was describing the formula, the isogeny formula, I kind of skated over some details. The first detail that I've omitted is that basically we are assuming that we have some torsion above like our kernel, but actually this is not like a strict condition. And in the paper we even show that you can relax this, and so you don't need this much torsion. You can just work using like only the kernel of this isogeny. And also another assumption that I've made before is that I'm computing isogenies whose kernel is kind of aligned with the theta structure. Well, what happens if the kernel is not aligned with the theta structure? What happens is that you need some new correction formulae, and the cost of this step actually requires like 100 multiplications, 8 squares, and 4 inversions. And then at the end of the chain, you will end up in the kind of the splitting isogeny, so which means that you will end up, in the kind of on this elliptic product. And on this elliptic product is represented in theta coordinates. But for most of the applications in isogeny-based cryptography, you actually want to work with like an explicit model for elliptic curves. And to obtain this explicit model, you need some conversion formulae. And these conversion formulae are not expensive, but I mean, like, I've not talked about these formulae, but these formulae are not expensive and are not by any means the bottleneck of these formulae. Okay, here I've just put like, I just want to conclude that just showing some timings. And yeah, so here we are working over a field, over the base field fp squared. And let's just look at like the first row. We implemented the algorithms both in SageMath and Rust. And in particular, for an isogeny, over fp squared, where p is like a prime of length 254 bits, and for an isogeny of length 126, then you have, I mean, these isogenies are actually the isogenies that you need in the case of like the variance of Ski-sign, especially for Ski-sign to the west. And the computational cost to compute like the codomain of such an isogeny is basically, it requires roughly like 2 milliseconds, and evaluating such an isogeny in Rust, it just takes like 161 microseconds. And this is actually the reason why actually the new Ski-sign variants are so efficient, and we can actually have like a Ski-sign version which is which is actually practical and competitive with other like post-quantum crypto systems, digital signature schemes. Well, this is all I wanted to say. Thanks for your attention.
Thank you very much, Luciano. We have time for one very quick question.
Thanks for the talk. So just one question. Can you go back to the table with the cost? Yes. If I'm not wrong, you are still using from the table the inverse from the gluing, no? So you didn't implement any projective version of the gluing isogenies, right?
Sorry?
Yeah, for the formula that you have in the gluing, the first isogeny, the first two isogeny.
Yes.
And it's still doing evaluations with inversions. Mm-hmm.
Yes, for the first isogeny, yes.
Yeah. Do you try, or do you have you ever implement the projective version of that? Because I think that will save maybe 70%, 15%.
Well, I mean, the gluing isogeny is just one isogeny that you compute.
No, but I mean in the full chain of the isogeny, because you are doing 1 to isogeny, the gluing, then you do, let's say, the general case, and then in the first step you are doing more than one evaluation of the isogeny because of the strategy that you are using. So if you remove that inverse, you're going to have maybe better timings. So do you try that, or any experiment on that?
We haven't tried that, but the 15% that you see is actually due to the gluing formula. So I mean, the conversion to compute like the correct theta structure. So the most expensive bit that you do at the beginning of your computation is basically that you take like the generators of your kernel, and you compute like a theta structure which is compatible with this generator, with these generators. And this is actually the most expensive step. I mean, like this step, probably yes, you can projectivize it and you can obtain something nicer. But I guess that the 15% that you mentioned comes from like this kind of adjusting of the theta structure. Okay. So yeah. But yeah, I guess you're right. Probably you can.
Yes, because I think you can do the same also with the pre-computation, with this 4 inverse, because you have 4 inverse also, 4 inversions.
Oh yes.
That you can do the same, and then I think that would give more speed ups.
Yeah, probably yes. Probably you're right. Yes. Yeah. It would be nice to see like what are actually concrete like improvements. Okay. To see any difference concrete.
Thank you.
Thank you. Thanks for the question.
Okay, in the interest of time, we are going to have to move to the next talk. So let's thank Luciano again. Okay, and for the next talk, we have Joseph, who's going to talk about extending the class group action attacks via sesquilinear pairings. The floor is yours.
Thank you. And thanks to the organizers for the invitation and organizing such a nice conference. I know it's quite a bit of work to put this all together, so thank you. Yes, I'm going to talk a little bit about extending some class group action attacks based on sesquilinear pairings, and this is joint work with Catherine Stang. So just a little bit of background to start. For the purposes of this talk, we'll take E to be a supersingular elliptic curve over some finite field F with characteristic P. K, capital K will always be an imaginary quadratic field, and O will be some order in K, not necessarily maximum. So then we just define a K orientation of our elliptic curve E to be some embedding of K into the endomorphism algebra, which we know abstractly is isomorphic to BP infinity, the quaternion algebra ramified at P and infinity. So if we consider this order O, and we consider its image under this embedding iota, then as long as that embedding actually lands in the endomorphism ring, we call that an O orientation. And if this embedding is maximal with respect to O, in the sense that iota does not embed some strict superorder of O into the endomorphism ring, we say that this orientation is a primitive O orientation. And we denote such a supersingular curve together with its K orientation iota just by this tuple. So we can then consider the set of primitively O-oriented supersingular elliptic curves up to isomorphism, and consider the action of the class group of O on this collection of curves together with these orientations. We can then define finite subgroups of these curves by taking some particular element in our class group, some particular representative, thinking about the kernels of all of the endomorphisms contained in that ideal, and taking that intersection. And what that allows us to do is it allows us to define an action of the class group. We simply take E in quotient by this subgroup we've created, and the corresponding orientation we get is the orientation that's naturally defined via this isogeny. So with this background in place, the sort of central problem to consider is what some in the literature call the vectorization problem. So if we take some orbit in the set of primitively oriented supersingular elliptic curves, primitively oriented by O, and we take two elements in that orbit, we can ask what element of the class group acts on E iota to give us E prime iota. And in general, it's thought that this problem is difficult. So the motivating question here is, we know that SIDH is no longer secure. This has been shown by Kastrick and Dekru, by Robert, Mano and Martindale, and by Mano, Martindale, Pani, Pope, and Wesolowski. A recent paper from 2023 by Kastrick, Halpin, Mertz, Mulo, Buren, and Verkauteren, which I will henceforth refer to as CHM+, wonders whether or not we can bridge the seeming gap between the SIDH attack and instances of the vectorization problem. So I want to start with an instructive example that will motivate some of what's been done thus far and some of what we did in our paper. So let's just assume that we have this following context. We have two curves, E and E prime over FP. They have a primitive orientation by Z adjoin square root minus P. And we have some secret FP rational isogeny whose degree is known. So if we then take some small prime L, we take some potentially large power of it, provided that L is co-prime to the degree of the isogeny, and that it splits in K, then we have this relationship between bases for this M torsion. Right? So under the isogeny phi, we know that phi sends p to some scalar multiple of p prime, and similarly with q. Now, if we consider the classical M-Weyh pairing, we would hope that we could gain some information on what this isogeny is doing by just pairing p prime with itself. Properties of our pairing imply this relationship. And given our assumptions, if we just work with some discrete logs, those discrete log computations would be efficient, and we might be able to recover lambda. However, the classical M-Weyh pairing is trivial when we pair a point with itself. So this idea of trying to use a pairing seems great, but at the end, we have this problem. So in CHM plus 23, the question the authors then asked was whether or not we can come up with some new pairings. And in particular, pairings that will be non-degenerate on some cyclic subgroup of E and that are compatible with oriented isogeny. And they managed to construct some of these pairings. And they find that in particular, these new pairings, which they call cyclic self-pairings, yield some efficient attacks on the vectorization problem, given the following conditions. One needs to know the degree of the secret isogeny, the discriminant of the relevant order needs to contain a large smooth square factor, and at times, if you need to perform the necessary computations, you might have to extend, perhaps significantly, the base field of the curves you're working with. I should note that there is some work in preparation by Kastrick, Dekru, Mano, Martindale, Penny, Pope, Robert, and Wesolowski that does appear to remove the square part of condition 2. So you may just need a large smooth factor. Okay, so I want to switch now to introducing a little bit about sesquilinear pairings. I should note that these can be defined purely formally, even for curves without CM. You can find all the details in the archive preprint sesquilinear pairings on elliptic curves by Stang. So to start, we have some imaginary quadratic order O, and we can represent the left regular representation of O acting on a chosen basis, 1 in tau for our order as follows. And similarly, we can define an action of this order on the Cartesian square of the multiplicative group of F crossed with itself. And we can then just construct this pairing. We don't yet have a pithy title for what this pairing is, but let's just refer to it for now as T hat. So what we do is we have our left regular representation of our order, represented by this 2 by 2 matrix, and taking some point in the alpha bar torsion of E, we can define the following functions, fp1 and fp2, by requiring that they have these two divisors. So we construct those functions, and then we define for f rational points, q, the following two divisors. Now, we choose R to be some sort of essential fudge factor. We choose this so that the supports of these divisors and of the functions that we just defined, fp1 and fp2, are disjoint for each ij pair. And now we can define the pairing as this product of functions evaluated at these divisors. And I just want to note for those of you who may be familiar with the definition of the classical Tate pairing in terms of divisors, this is a somewhat natural extension of the Tate pairing. If we define fp just to be this product of fp1 and fp2 acted on by tau, and similarly define dq to be the sum of these two divisors where tau is acting on dq2, then we can think of this pairing as just fp evaluated at the divisor dq. So this pairing that we have constructed has a couple of key properties. There are some additional properties that aren't immediately relevant for this talk, but the ones I'll mention here are sesquilinearity. So if we take t hat and we evaluate at gamma acting on p and delta acting on q, that's going to be the same thing as taking the pairing of p with q and raising that to the product of gamma and delta. Excuse me, gamma bar. That's where the sesquilinearity comes in. They're also compatible. So if we have some oriented isogeny phi, then we have this nice relationship here between considering t hat acting on applied to phi p and phi q, and t hat just applied to p and q. And finally, these pairings are in many cases non-degenerate. So as long as we satisfy the conditions listed here, and crucially, this last condition such that P acted on by the order O is the N torsion. In other words, as long as the N torsion is cyclic as an O module, then we will have some non-degenerate pairings. So I should note these pairings are efficiently computable via a Miller-style algorithm. The details are in the paper of Stang that I mentioned earlier. And oftentimes, as one would do with the Tate pairing, you can come up with a sort of reduced version of this pairing so that your values actually are in the roots of unity. So you can apply this final exponentiation. Now, the key idea here behind all of this construction is that these sesquilinear pairings respect the O module structure of these torsion subgroups, not merely their Z module structure. And so this is what yields new instances of some non-trivial self-pairings. So recall that in the statement of non-degeneracy we had just a moment ago, one of these conditions was that our chosen torsion subgroup, the N torsion, is cyclic as an O module, where N is the norm of alpha. And there's a fairly straightforward extension of some results of Lenstra that tell us that we can characterize when we have cyclicity in certain cases. So if we have some O-oriented elliptic curve, and if F is the index of O in the primitive order, what in the paper we call the relative conductor, then the M torsion will be cyclic as an O module, provided that M is coprime to this relative conductor. So there are many cases where this cyclicity condition is satisfied. And so this in turn is going to yield some non-degenerate self-pairings. Now, there's a lot of conditions here in this theorem, but the key point I think we should take away for now is that in particular, if the M torsion we're working with is cyclic as an O module, then not only will the self-pairing of this generator point be non-trivial, it will in fact be of maximal order. So if we consider pairing of O module generator point P with itself, that self-pairing will have order n. Okay, some computational assumptions for the result I will mention shortly. Whenever I say efficient from here on out, I mean polynomial in the size of the input. That's both polynomial in the log m in the torsion and in the cardinality of the base field. When I say that we have an O-oriented curve, I mean we have an explicit orientation. So if we're given some alpha in the order, we can actually compute its action on a point P on the curve efficiently. We assume also that the degree of the hidden isogeny is known. And finally, we assume that M is fairly nice. Not only is it coprime to the characteristic of F, but it's smooth. So this will allow us to assume that discrete logarithms are computable in polynomial time, and that we can efficiently write any element of the M torsion in terms of a given basis. So if we make just a slight modification of the sesquilinear pairing, we still retain several of the nice properties that we would like. In particular, this pairing remains non-degenerate as long as the M torsion is cyclic as an O module. And we have the following result. So if we take some degree D isogeny between two curves E and E prime, if we also assume that M divides the discriminant of this order, and that there are polynomially many square roots of 1 modulo M, then there is some efficiently computable point Q on the M torsion that is of order M, and there's some polynomial size subset of the M torsion on E prime, such that the image of Q under the isogeny is computable in polynomially many operations in the field of definition of the M torsion. So it sits inside this subset S. So the significance of this, right, is that if we have knowledge of the image of Q under phi for an order M point, then the O module structure of EM, in particular the fact that it is cyclic, will together with knowledge of the image of phi yield knowledge of phi on all of the M torsion. And of additional significance, we get to exploit the O module structure to allow for computations taking place strictly over the field of definition of M, as opposed to over the field of definition of M squared. And this is what allows us to obtain some additional polynomial time attacks on instances of the vectorization problem. I just want to say a few words about the proof for this result. So one can show that there is some element tau in the order, such that modulo M, Z adjoint tau, is equal to the order. And furthermore, that the norm and the trace of this element tau are congruent to 0, mod M. We also have, just from the properties of our modified sesquilinear pairing, that if we take the self-pairing of P with itself and raise it to the degree of our isogeny phi, that's going to be the same thing as taking the self-pairing of P prime with itself and raising that to the norm of some element lambda. And furthermore, if we take lambda to be congruent to A plus B tau modulo M, this will be the case given our previous assumptions, then, sorry, that should be, that M prime should be an M here. Then modulo M, the norm of lambda will be a square. And what this tells us furthermore is that the image of tau P under phi is just going to be A times tau applied to P prime for some A. Now our assumptions on M, namely that there are only polynomially many square roots of 1, will imply that the set of possible values of A is efficiently computable and of polynomial size. So you just work through the possible candidates for A until you've found the correct one, and now you know the image of this point under phi. So a quick example, this is adapted from some correspondence that my co-author Kate and I had with Wouter Kastrick. If we take this particular model for 1728, and we have P to be congruent to 3 mod 4, and in particular be 4 times 3 to the r minus 1, then 1728 is in fact supersingular. And if we denote the Frobenius endomorphism by pi sub p, then we have this element tau in our endomorphism ring. Now one can show, it's just a computational check, that the norm of tau is 3 to the r, and that the trace is 0. So if we take our imaginary quadratic order to be Z adjoin tau, the norm is going to divide the discriminant. So let's take M to be 3 to the r. That means M divides the discriminant. One can also show that the FP squared rational torsion of E is in fact z mod p plus 1 squared. So this tells us that the 3 to the r torsion is fp squared rational. And what this means then is that all of our pairing computations can take place in the fp squared rational torsion. Now, if we also assume that m is greater than 4 times the degree of the isogeny, this will tell us that the SIDH portion of any attack would be efficient as well. And so this is going to give us a new instance of efficient attacks on the vectorization problem. In fact, this example is in contrast to the methods from CHM plus 23. There, one would need to move to the field of definition for the 3 to the 2r torsion. And this degree grows exponentially with r. Okay, that's all I'm going to say about my paper for now, so thank you.
Thank you very much. Are there questions?
Thanks for the presentation, really nice. Just quick question, is there is any restriction between the codomain of the elliptic curve? For example, between E and E prime? Any restriction between them?
Beyond just...
For example, they cannot be isomorphic or something like that?
No, I don't think so.
Okay. Thank you.
Any more questions? Okay, lest we be left on the ground while the rest of the conference soars on the river, I think it's time to stop this session. So let's thank Joseph again. And